Hello everyone, so welcome to week 4 of this course, Deep Learning for Natural Language Processing. So in this week we will be starting with one of the first major architectures for deep learning for NLP. This is recurrent neural networks. We will talk about recurrent neural networks for language modeling in this lecture, and then we will proceed towards other applications of recurrent neural networks in the subsequent lectures in this week. So what are we going to cover in this lecture? So we'll talk about a neural language model. So till now we talked about the language modeling as an n-gram language model, the classical NLP. But what do we have to do towards going for a neural language model? And then we will progress from there to recurrent neural networks. We'll provide some intuition behind this network, and then we will talk about language modeling based on recurrent neural networks. So that will be this lecture's content. So quick recap. So you all remember language modeling from our very first week. So we discussed what is language modeling. So suppose you have a sentence, the students open there, and you want to predict the next word. And this can be any word, say from books, laptops, exams, minds, or something else, right? From your entire vocabulary. You do that, or you find the probability of a sentence. So these are called language modeling. Finding probability of a sequence or finding the next word given the previous sequence. And we used n-gram language models for this. Now, what are the issues with n-gram language models? Suppose you used n-gram language model, you actually had this phrase already there in the data, the students opened there, and you could figure it out, then this is books, right, maybe. But in n-gram language model, each word is treated independent, right? So if you have learned something for the students opened there, say the students opened there, and you learned it is books, by your parameters that the probability of books given students opened there, let's say it is high, and you can predict the word books in this case. But what if you get some different context, I mean same context but different terms, like some synonyms, right, or different way of putting the same context. So let's say your sentence is the pupils open there, and now whatever you've learned for students open there, this will not be transferable to pupils open there. I cannot just transfer that knowledge, even if I know, I mean, first of all, I do not know directly that they are synonyms unless I have some other model to tell me that. So right now they are two orthogonal words, and they don't share the information among each other, right? You may have different synonyms like scholars open there, undergraduates open there. You may have, instead of opened, you have students turned the pages off there, students attentively pursued there. Right, so you may have different variety of context in language, but whatever you learn from one particular context would not be transferable. So now, how do we share the information across this semantically similar prefixes? Right, that is the major problem, and that is where the neural models help us in achieving generalization. Okay, so that is what we want to achieve. So we want to say, okay, I have this phrase students open there, but I don't want to directly use a model like n-gram language model that looks only at the word surface forms. But I instead want to use a neural language model that can also generalize to synonyms and similar phrases that have been put in different surface forms, but they mean the same. So I want to have a neural language model that can do this prediction of the next word, that is books. Okay. Now, how do we do this, right? So first part is, how would I even feed this information students open there? Right? So what we have learned in week 3 is that, so these words, if I want to generalize, I can convert them into their word vectors, embeddings. So what I can do, I can obtain the embeddings for these vectors. Say students open there, so these are the word embeddings, word vectors. And then I have some neural network that will take these word vectors and produce some representation. So this you can call it as the phrase representation or the sentence representation at this point. So you can call it the phrase representation. And that is the powerful idea that we have in deep learning, that you can achieve representations that are in form of vectors, right? So this is just a vector, and that is representing the information that you have from the 3 words, students open there. So you applied a neural network on these embeddings and you obtained some representation, right? So you did some composition of the word embeddings and you obtain this composed prefix representation. Right? From there, now you want to predict the next word. Let's say you want to predict the books. Okay. So this is the problem setting now. You have some input words, you're trying to compose them into a single representation, and then you want to make a prediction from that. Okay. So how does that happen? So let's talk about the second part. So let's say there is some way in which you could compose these words and obtain a low dimension representation of this phrase students open there, right? So let's say this is the vector that you obtained. I want to do a prediction from that. So how would I go about that? This is typically how we do classification in machine learning. So what I will do, I'll say, okay, next word prediction is just a classification task. So I may have any word in my vocabulary. So I have vocabulary of size V, and I have words starting from A to J, right? All the V words, lexicographical ordering. And I would have books also indexed at some point. I will have laptops and some other point and so on. All the words would feature somewhere in my vocabulary, right? So what I will do, I will predict a probability distribution over the entire vocabulary. So that is probability of the ith word given the vector for students open there. So I have the vector, given this vector I want to find the probability for each word wi in the vocabulary, for all word wi in the vocabulary. Okay. So it can be books, laptops, or any other word. So this is what I want to do, right? So how does that happen? Okay. So let's take a simple toy example. Let's say our vocabulary is very, very small. We have just 4 words: books, houses, lamps, and stamps. I have only 4 words in my vocabulary. That means my output will be 4-dimensional, right? And so I want to achieve a probability distribution at the output. Let's say this is one possible distribution, 0.6, 0.2, 0.1, 0.1 for books, houses, lamps, and stamps, right? Adds up to 1, all are greater than or equal to 0. So you want to get this probability distribution over these 4 words. And what is our input? Input is a composed phrase representation. Let's say that's also just 3-dimension representation. And this is my input, minus 2.3, 0.9, and 5.4. So I have this input. I want to predict a distribution, a probability distribution. So how would I go about that? So what you will need to do, we will need to multiply this. So we have this 3D prefix vector. I have to project it to 4 dimensions. So for that, I need a matrix. So I need a 4 cross 3 matrix. 4 cross 3 matrix that will project this 3-dimension prefix vector to 4-dimension output, right? So this, when I multiply W with X, so this is 4 cross 3 times 3 cross 1, I will get a 4 cross 1 vector, right? So I have to do W times X. Right? What is this W? This is just a weight matrix that contains various parameters that we can modify, we can update during our training process with gradient descent. So we can update these parameters to control the final probability. So depending on the loss that I will get, I can update my parameters, right? And they will control the probability of the word. So I can tune my parameters, learn them well so that they can start predicting a correct word. Okay? So I have this 4 cross 3 matrix in this toy example. Now, so what is the intuition? So, you see this is 4 cross 3, what are the rows corresponding to? So, there are 4 words in the vocabulary. So, the rows correspond to individual words in the vocabulary. Okay. So, like this row corresponds to the word stamps, right. So, you can think about the row as containing some sort of feature weights for a corresponding word in the vocabulary, and that weights is what you have to learn. Okay. Similarly, this input representation, the phrase representation x, can also correspond to some feature of the prefix that you have learned. Okay. So, now that you have this intuition, you have this weight matrix, you have the composed phrase representation x. What I will do, I will simply multiply w with x. Right. So, I simply multiply w with x. And how does that happen? So, you have multiply this whole row with this entire column. Right. So, you will put this minus 2.3, 0.9, 5.4, and you will multiply this. So, the first output will be 1.2 times minus 2.3 minus 0.3 times 0.9 plus 0.9 times 5.4, and this comes out to be 1.8. Similarly, you can get the output for the other 3 dimension. I will multiply the next row with this column, I will get minus 11.9, 12.9, minus 8.9. So, this is how we compute the dot product of w and x, and I get this output. Okay, great. So, we started with a vector, and we have found a way in which we can convert into 4-dimension output. Still, it is not a probability distribution, right. So, this is just some numbers, even some negative numbers. So, how do I convert into probability distribution? So, we have this standard trick of Softmax. So, if I have some numbers x1 to xn, any real numbers, I want to convert into probability distribution, I just take a Softmax. So, I will take e to the power these numbers divide by sum over e to the power xj. So, I apply a Softmax over that. So, I do the same. So, I take these numbers and apply Softmax, and you see this would get the highest probability because this is the highest number, right. So, this actually gets highest probability 0.73, 1.8 gets the next high probability 0.24, and the other 2 words get very low probability, and I get a probability distribution finally, right. Of course, this is not what we desired because we wanted to get books, but we are just training the model. So, we are getting lambs at this point, does not matter. I will find the loss from here. So, that will be minus log probability of the correct word. So, minus log 0.24 will be my loss, right. So, this you can see is a positive number, right. So, roughly like minus log 1 by 4 roughly. So, which is log 4, right. It is a positive number. Yeah. So, you get some loss, use that to update your parameters. Right. Okay. So, this is what is done, right. So, you have, once you have this representation for the 3 words students open there, I can use a matrix multiplication to predict the probabilities, right. So, now once we know this part, let us see how do we compute the prefix representation. So, given these inputs, how do we obtain this prefix representation? And actually there are multiple ways of doing that, right. So, this is what we will define as the composition functions. So, you have a sequence of words, right. You can use their vector embeddings and so on. So, you have a sequence of word embeddings corresponding to the token of a given prefix. This is your input. Output is you want a single vector, right. So, once you have a single vector, everything else is like clear, that how would you predict the next word. The question is, how would you compose the sequence of word embeddings into a single vector, right. And there you can use multiple composition functions. For example, you can use element wise function, like you can just sum over all the word embeddings, just take an average, right. You can just sum over all the embeddings or take an average, or you can use other things, other composition functions, right. So, some element wise functions can be used. I can concatenate them, right. I can do concatenation. So, what is the benefit I get from concatenation compared to average? Average does not preserve the word ordering, right. So, you will just, if the word occurs anywhere, you will just average that, right. It is like it becomes a bag of words. But with concatenation, you can preserve the word ordering. You will know, okay, which word come at the, say, first position, then the vector for the second position, third position, And composition means you will just append it to each other. Say each vector is of dimension d, and you are using 3 words, so you get a 3D dimension vector after composition. While averaging in sum, you will get the same dimension, just d dimension through average and sum. You can use other things like feed-forward neural networks. You can use convolutional neural networks on top of this representation. You can use recurrent neural networks. That's what we will see today. And you can also use transformers, right, that we will see later in this course. So let's start discussing simple concatenation, the first neural language model, that how would you use that to obtain a language model that can predict the next word. Okay, so let's first look at the concatenation. So let's say we have a very long phrase, right, in general. As the proctor started the clock, the students opened there, right? And we are talking about a fixed window neural language model because we are concatenating, and because you are concatenating, you need a fixed dimension, right, that you can tell your model that I will take the last 4 words. It's like if saying it's a 5-gram model, you are taking the previous 4 words as the context, and I want to predict the next word, right? So idea is simple. You will concatenate the embeddings for these 4 words, and you will use that to predict the next word. Right? Okay. So what we will do? So we have the students open there. I obtain their word embeddings. So this is embedding for the, embedding for students, opened, and there. I have concatenated. Let's say each one is of dimension d. So I have 4D dimension representation of my input layer. This is my input layer. This is 4D dimension. Next, like I do in the normal feed-forward neural network, I'll have a hidden layer. Let's say it's of dimension h. And I have matrix from input to hidden layer. It's something like W times E, if E denotes this input, plus a bias term. And I apply some nonlinearity, something like a tan h function or a ReLU function. I apply some nonlinearity, and I get the hidden layer representation. And then once I have the hidden layer representation, that acts as the vector I was talking about, right? So once I have this vector representation, this is the vector, I can do the normal thing. I'll apply another matrix U that will project it to the entire vocabulary. So I'll do U times H plus another bias. I get some real values of dimensionality V. And to convert into probability distribution, I again apply softmax, right? And this gives me a probability distribution in V dimension, right? That will be the entire process, and that's how I can get a fixed window neural language model, right? Now, what are the advantages of this neural language model? So first of all, compare it. Say it looks like a 5-gram language model, right? So you're using the previous 4 words and predicting the next word. So how many parameters you had to store for a 5-gram language model? So we said in theory this can be V to the power 5, right? Because you have probability of word I given the previous 4 words. And you can take all possible variation. This will be of the order of V to the power 5, exponential in the vocabulary size. How many parameters you need in this model? So I need 4D times H for going from input to hidden, plus the matrix U, that is H times V. Now we know D is a very small vector. So when we do embeddings, typically they are much smaller than the vocabulary size. And H would also be much smaller than the vocabulary. So this will be approximately H times V, right? So it's just linearly dependent on the vocabulary, right? It's dependent linearly on the vocabulary times the hidden vector size, right? That's all. That many parameters plus of course 40 times H is what you need. We are ignoring bias terms. They will not be too many, right? So that many parameters you need compared to V to the power 5, so, right? So it's a very efficient learning. And then come back to the same point that instead of the students open there, suppose I replace students by the peoples open there. It's okay. The learning will be transferable because pupils and students are typically going to have very similar embeddings. So pupils will have very similar representation. So whatever was learned for the students will also be transferable to pupils. Right? So that would be helpful too. Okay. So yeah, so these are the improvements. There is no sparsity problem. So you have very small number of parameters. You don't need to store all the objects and blah. Now, what are the issues with this model? Then why would we have to go for something better like recurrent neural networks? First of all, we are still talking about a fixed window. So we are saying 4 words before, right? Of course, you can enlarge window length, right? But then your matrix W will also become larger. As you keep on enlarging the window size, it will become larger and larger, right? And you can never say what is the large enough window, right? So whether I will use 10 words, 15 words, 20 words, you can never say what is the optimal window, right? And yeah, once you have actually used a larger window, you have to use all the words, right, in the context, even if they are not relevant. So this is one problem, like how do you know what is the good window? Then the another problem is that although it solves the problem that instead of students you have peoples, it will still work. But what if you change the order, right? So you are here x1 and x2 are multiplied by very different weights. So the weights that x1 is multiplied by is very different to the weights that x2 is multiplied by. So learning something for the occurring in the first position and students occurring in the second position. What if the sentences students have opened there? So students come at the first position, right? So whatever you have learned from the second position, these weights will not be transferable to the weights at the first position because they are different weights, right? So you can think of this 4D times h as d cross h, d cross h, d cross h, d cross h, 4 different weights. So whatever you have learned in this position will not be transferable to the another position. So that is a problem. Right? So then can we have an architecture that can process any length of input? That's the question. And that's where the recurrent neural networks come into picture. Right? So what will they do? So let's look at the sentence. The students open there. I'll still get the word embeddings. So let's say x1, x2, x3, x4 are the word embeddings. Remember, I want to get a fixed vector representation from this, right? From this whole prefix. So what do I do in the recurrent neural networks? I start by a recurrent hidden state. So hidden state keeps on updating as I get more and more input. So I start with an initial state. So this is my initial hidden state. And then I keep on updating it. So I'll say, okay, I'll feed this input and the previous hidden state, and I'll get my h1. How? So this is simply that tth time this depends on u times ht minus 1 plus w times xt. So I multiply this vector with u and the input with w, plus of course there's a bias term, and apply some nonlinearity. It can be 10h, for example, or LU. And I get my new hidden state, right? And I keep on doing that. So I don't need new parameters. Once I go to students, I'll use the same weight matrix. This is shared parameter. I'll use the same U matrix, and I'll get H2. Like that, I'll get H4. And this becomes my fixed vector that I will use for predicting the next word. This is my final vector representation of the entire prefix. Okay. And now I don't care how long a window is, because I can keep on obtaining my H4, H5, H6, H10 without having any additional parameters, right? And because we multiply each position with the same parameters, even if you change the word, it's not change the vector too much, right? Even if you change, they are multiplied by the same vectors, right? So something like that. So you have initial hidden state, you multiply with U, and you multiply the input with W, you get your H1. Same way you get your H2 and so on by applying this particular forward propagation. And you go up to the last word in your prefix, you get the final representation H4, and now you know the next process. You will multiply this with the matrix V. This will project into the vocabulary dimension. I'll apply softmax and I'll get a probability for the entire vocabulary, right? Each word in the vocabulary, I get a probability. Okay, so how is this different than the previous model, the fixed window neural model. So first of all, you can process any length sequence, right? At least in theory, you give any sequence length, it should process and give me a vector representation H4. So even if you increase the input length, the model size doesn't increase. You have the same model size. What is the model size? You have U, V, and W. That's all. These three learnable matrices, nothing else. And at any time t, computation can use information from many steps, right? And whatever steps you are, H3 stores all the information that is seen till now. H4 stores all the information that is seen till now, and so on. And weights are shared across time steps. Right? So representations are shared. So so just formally, what is your recurrent neural network? So you know this normal neural network, you have an input layer, you have a hidden layer, you have an output layer. In recurrent neural network, you can update this hidden state in a recurrent manner. So you have the old state and the new input, and you use a function with some parameters to update this to new state, right? And you can keep on doing that, right? The same function and same set of parameters are used at every time step. So that's what recurrent neural networks are, right? And if you try to visualize, is another way of visualizing this. So this, if you would have seen just this, that would have been a vanilla neural network, simple feed forward multi-layer perceptron or simple vanilla neural network. What happens extra in the recurrent neural network is that you also feed the previous time step as another input. So you can think of it as if you are concatenating the previous time step with the current input and feeding it to the network, right? So this has a matrix U and this is a matrix W. They have different parameters, right? That's okay. That's what we saw in the 4 words in the fixed window neural model. So each position had a separate parameters. Here also, you can think of it like you have 2 different inputs, the previous state and the current input, and you have 2 different parameters, the matrices U and W. And you do U times HT minus 1 plus W times XT to go to HT, and of course you apply some nonlinearity like 10H or value or something. And you get HT, and then from there on, the process is very similar to what you have in the normal neural network. You just apply this V matrix to get the final output layer. Okay, so forward propagation we saw HT depends on HT minus 1 and XT using these 2 parameters. And then once you get HT, you can apply, add a matrix, multiply with the matrix V to get the final output. Okay, and let's say the dimension of input, hidden, and output are these. So what are the parameters you need? You need a matrix W that is going from input to hidden, so dH times Tn, matrix U that is going from hidden to hidden, and matrix V that is going from hidden to output. So that's all the parameters that you are needing in recurrent neural networks, and that's what you have to train, right, for training a recurrent neural network model. Of course, this all ignores bias terms, but you can just add some bias terms if you need. Right? Okay, so this is how RNNs look like when you unroll them in time. So you started with the initial hidden state, you have a new input and you get the new hidden state, another input, another hidden state, another input, another hidden state, and each time you have a flexibility whether you want an output at each point. If you want an output at each point, you apply this matrix V and get the outputs also. But if you don't want output at each step, we will see examples, then you can just apply this matrix V wherever you need the output, right? So this is how RNNs can be seen unrolled in time. Okay, so you can try this small problem. So suppose you are predicting the next word from a sequence of words using an RNN. Okay, suppose it's a toy problem. Suppose that you have only 5 words in the vocabulary, and the representation is just 1 hot, no word embeddings in this problem, right? So each word is a 5-dimensional representation. So hidden layer has 6 dimensions. So what are the total number of parameters you will have to learn, right? So your input is 1 hot, X is 1 hot, so you have 5 dimensions. Your hidden layer is 6 dimensions, and your output is 5 dimensions. Right? So what are the parameters you need? You want to go from input to hidden, the matrix W, so that is 5 cross 6. You want to go from hidden to hidden, H1 to H2, that will be matrix U 6 cross 6, and you want to go from U to Y, the H to Y, that will be the matrix V 6 cross 5. Right. So, the parameters you need are 30 plus 30 plus 36, so 96 parameters. Right. Very small for this toy problem. So, only 96 parameters, ignoring bias, of course. Okay. Now, how do you train this RNN language model, right? So, see, language modeling you can train just by self-supervision, because you just need data, and whenever you have a corpus, you can say, given the previous prefix, what is my next word? You can easily say that, right? So, we will just take a corpus of text as the training material. At each time step t, we know what is the current prefix we have seen, and we ask the model to predict the next word. So, just predict the next word, okay? And we already discussed this. This is called self-supervision because we don't need any gold data, not any human label data. So, this is just the natural sequence of words they themselves supervise for this model. And we train the model to minimize the error in predicting the next word, right? And this typically is the cross-entropy loss. Because we are predicting a probability distribution, we will simply say minus log probability of the ground truth token, ground truth next token. So, minus log probability of a ground truth token. That is my loss, and that's what I accumulate over multiple time step and use back propagation to train my model. So, something like this. So, you will say, suppose you have a corpus sentence, so long and thanks for, and you predict the next word, say all, right? This is the ground truth token. So, what you will do, you will keep on accumulating. So, you apply, this is the embedding for so, you multiply with this matrix W, right? You have some initial hidden state, you multiply with U, you get the hidden state H1, then you multiply with V, this H1, you get a probability distribution by Softmax, and you find out what is the probability for the ground truth token long, and you take minus log probability of that, and that becomes your training signal, the loss function here, minus log probability of this. Again, but next time whatever word has the highest probability, you will not use that, you will feed this correct word again, okay, and to predict. So, this particular phenomena is also called teacher forcing. We will discuss this in detail. So, teacher forcing. So, where although you may predict a different word, you actually feed the ground truth token next step, right? So, that it knows the correct ground truth token, it predicts again, you compute the minus log probability of correct token, and you accumulate all of these losses that you are getting at each time step, right? Divide by the number of time step, and this you use to update your parameters. What are the parameters? Just 3 matrices U, V, and W. Okay. So, fine. I mean, so this is what is an introduction to recurrent neural networks. So, you can read more about this in chapter 8 of our book. And the next lecture, I will discuss about further applications of RNN. How do you use it for, say, generating text, classification, sequence labeling, and so on. Okay. Thank you then.